All right. Welcome, everybody, to our annual update to the algorithms workshop. Can you believe it has been 5 years since the algorithms workshop? You can do it. Yes. This is not going to be an introduction to the Rubin data management science pipelines. If you are new to the science pipelines, I highly recommend that you go to ls.st/LAW, LS, that stands for LSSD Algorithms Workshop. We have a number of talks that are all still relevant regarding our plans for approaches to different algorithms. We even have a high-level talk of an introduction to the science pipelines. For the rest of you who have been following along for the last 15 years, we've got a number of Science Pipelines team members in person available to answer questions. And we've prepared an update where we are, what we're paying attention to now, what performance looks like on LSSTChem data, hot off the press, and what we have planned for this upcoming year. We also have special guest Tatiana Acero Cuellar talking about the real bogus reliability work that they've been doing this year as well. We have a number of folks on Zoom as well who are available to answer questions. General plan is we're going to give a talk that's about an hour, and then we're going to have 30 minutes for questions at the end. I ask you to hold your questions at the end until the end. If you have something pops into your head, write it down, save it, and then we will direct your question to whoever knows most about that topic. Please don't use Zoom chat to ask your questions. We have a Slack channel that Erfan and Brianna are monitoring, and that's the best way to get your questions into the question and answer period at the end. And we'll also be running around microphones at that point. All right. Okay, I am introducing the LSST Science Pipelines team. We are the 20 or so scientists that are responsible for writing the software that takes the raw images coming off the telescope, calibrates out the effects of the atmosphere, the instrument, to provide science-ready catalogs and images. We all come from different science backgrounds, but we're unified in our belief that our best contribution to Rubin observatory science is making the measurements that you rely on, the light curves, the galaxy shapes, and all the other measurements for your science. If you are in one of the commissioning science units, then there's a 60% chance that one of us is your science unit lead. That is going to be a problem. For years, we have used precursor data sets to validate the algorithms. And we are very, very grateful to these precursor data sets because now we can use these. Because we have validated them on precursor data sets, we know that we can use these algorithms to validate the system. And I'll tell you more about how this works in a sec. You're not going to see any performance plots with precursors in this talk because we have real data now. So I'm not going to bore you with talking to you about our regression testing and how we compute performance metrics on weekly and nightly cadences with our releases. The pipelines are made up of tasks. Tasks are the building blocks of pipelines. These building blocks can be assembled into an alert production pipeline, a data release production pipeline, a calibration pipeline, and a new one that you'll hear about this talk is the nightly validation pipeline, which is it's data release flavored, but only consists of the single frame processing and then some roll-ups at the end to characterize the data taken last night. This pipeline is a commissioning special for supporting commissioning and giving people a view of the data taken last night. The pipelines not only process the data, but they also evaluate themselves as they go. They do this by having certain tasks which have no other responsibility than computing a scientific performance metric. Some of these metrics are low level that probe just one thing. For example, astrometric repeatability probes the astrometry. Some of these metrics are more high level and probe many things at once. One example of this is the number of DIA sources in the difference images. This is a proxy for the number of false positives, which can explode for a number of different reasons, because of problems in the backgrounds, in the problems in the PSFs, problems in the variance plane, could be anything. Another high-level metric and plot is the stellar locus, for example. If you plot R minus I versus G minus R, point sources will collapse into a locus. And if the width of that locus is wider than the intrinsic width due to stellar variation, then you know you have a problem. That problem could be from a number of different aspects in the algorithms. It could be photometry, astrometry, PSFs, you name it. The plots that are output from the pipelines also have a metric, a summary metric written on them. That summary metric we also visualize as a function of position over the sky. And we also dispatch it to Sasquatch, the Rubin Observatory telemetry service, for storing, it's among other things, it stores the science quality metrics. If we keep the data fixed, then these metrics can track pipeline quality over time. And we did this all through construction, and we're still doing this now, where we have a curated data set that we run on monthly, weekly, and nightly cadences and to track scientific performance of the algorithms as a function of version. But you can also use the same metrics to probe image quality. If you hold the pipeline fixed and vary the data, these same science quality metrics can be used for assessing the hardware, the cadence, and everything that we're trying to verify during commissioning. This is exactly the dance that we're trying to do right now. We're doing both at the same time. So the way this works is, even though we have verified that the algorithms work on precursor data sets, for every new camera, telescope, cadence combination that we run the pipelines on, they require a short commissioning period for themselves. We need to take time to write software that mitigates all the new detector effects that we've never seen before. We need to combine calibration frames. We need to build illumination correction models, camera distortion models. We need to tune config parameters to respond to the true variation of different quantities like the PSFs over the focal plane. The science quality metrics, they have contributions from both the pipelines and the hardware. And it's only by going through this pipeline commissioning process and dialing down the contribution from the algorithms that we can reveal the capability of the true as-built hardware. And in the same process, we are also providing you the best possible data preview too. And so we're going to show we're in this process right now. The commissioning process for the pipelines for ComCam is behind us. That was released as part of Data Preview 1, and we are in the midst of LSST-CAM commissioning as we speak. So the plots that we're going to show for the rest of this talk are going to have ComCam data and LSST-CAM data. You won't see any precursors. We went on Sky with ComCam in October and selected a number 7 fields that span the LSST science themes and probe different parts of the LSST pipelines. We have some crowded fields, some with saturated cores. We have an ecliptic field, a dense Dillard star field, and some extragalactic fields. Those are the extended, the Euclid deep field south, and then the extended Chandra deep field south. So those were the 2 fields that we had the highest expectations of the performance of the pipelines. And I believe most of the ComCam data that you'll see for the rest of this talk focuses on the extended Chandra deep field south. Each of these, the ComCam field of view was quite, quite small compared to that of LSST-CAM. And each field covers only a couple tracks and only partially at that. So to build coads, we split up the sky into a so-called sky map. That sky map consists of tracts, which is then subdivided into patches. Tracts are roughly 2.5 square degrees. And so if you see tract 5063 in the rest of this talk, that is the tract with the most coverage in the ECDFS field for ComCam on sky period. I mentioned earlier that we can also visualize these metrics over the sky. This is stellar photometric repeatability in the R band for ComCam. It covers only 25 tracks and only partially covers these 25 tracks. These were some hard-earned tracks. We took ComCam off sky and then worked really hard on providing the best pipelines for data preview 2, which yielded version 29, and then got ready to go on sky with LSST-CAM. And we were ready. We had the alert production pipeline on the prompt processing framework ready and waiting. Any image that rolls off the telescope would get automatically processed by that. Even though the alerts aren't being distributed public, they are being generated internally. We have the nightly validation pipeline going, which summarizes the data from last night and provides post-ISR and single visit images. And we have these biweekly data release productions that are going, that provide the full suite of data products for people working on commissioning and allowing them to verify or work on their component. So we go on sky April 15th, and then we get back the results for the nightly validation from the nightly validation pipeline, and it looks something like this. And I know we were working on building a telescope with an enormous field of view, but still seeing us cover this much area without even trying blew my mind. And I want to hear from you if there were any moments over the course of the past year when we were commissioning that something surprised you, or you realized something for the first time, or you understood something for the first time via whatever mechanism. So if you have moments like this, like I did, I would love to hear about them during the coffee breaks, or write me on Slack. We then undertook the mission of taking some data for a first look. This is the M49 field, which is approximately 2 focal planes worth. This image is a HIPS map built on the coads. It's a zoomable, pannable, hierarchically tiled image, RGB image of our coads. And we generate these HIPS maps for every data release production as a QA tool, because there's no better way to find whether you missed clipping satellites or asteroids in your coads than just looking at the image with your eyeballs. If you haven't checked these out yet, there's a number of different options for looking at the HIPS maps. That we have data preview 1 HIPS maps that you can look at via the portal. And if you're on the commissioning team, we generate these every couple of weeks with the data that's available from LSST-CAM. Since Rubin first look, we have been working hard on pipeline commissioning. The data that has been taken so far for pipeline commissioning, it at first focused on these field surveys, much like we did with ComCam on Sky. We focused on building up depth in certain regions of the sky that probe different science cases and different parts of the pipeline. We have Cosmos, and I've heard this conversation this morning implying that we haven't taken Cosmos data yet. We actually have hundreds of visits of Cosmos already. So rest assured, if you want Cosmos data, we have it. We have data in New Horizons and a field that we call the hex grid field. This was meant to serve as templates for the on order of thousands of square degrees SV survey that we're working on right now. But the image quality and didn't allow us to build up the depth that we needed to build to templates for that yet. And then finally, SV 225 -40, which if you're an observer, you know this as block T460. This is our dense Dillard star field. It has the stellar density 10 times larger than a typical high galactic latitude field, has appropriate ditherings. This data was taken primarily for commissioning the astrometric and photometric calibration algorithms. And I believe there's 85 million stars in this field, which is a lot of stars. I think this also provided surprises for team members as well. And then one final note about the data. On April 15th, you'll see full focal plane residuals in the rest of the talk, and you'll notice that sometimes there were some CCDs missing. In the very beginning, there were 6 CCDs missing. We brought 3 of those online by May, and then since then we brought 2 more online, but they're not out of the embargo period, so I can't show you. And now we're going to do a whirlwind tour of all the algorithms, their scientific performance, and what we're worried about now. So I'll hand off to Alex first.
Okay. Hello, I'm Alex. I'm a postdoc at SLAC, and I work on the instrument signature removal part of the pipeline. So once a raw image comes off the camera, this is the first thing the image sees. So the main thing for LSST is the ISR task LSST. This is the first step in the data reduction pipeline. And the goal of the ISR task is to take the entire photon transfer mechanism from when a photon hits the CCD to when it actually gets read out, and do that process in reverse and remove all the instrument artifacts and distortions that aren't of astrophysical origin. So currently, our model of how that process happens came from a long back and forth discussion between DM and the camera team. And we've come up with the most physically realistic model, we think, what happens when a photon hits a CCD. And what we now have is corrections for almost everything in here. So we have things for physical defects, charge transfer inefficiency, high signal nonlinearity, linear and nonlinear crosstalk, brighter, fatter traps, and many other things. And currently, this is the default task that's being run on all LSST camera type detectors. So that includes, of course, the LSST camera focal plane, but also the auxiliary telescope, which has a single LSST cam CCD and ComCam, which went into DP1. So during ComCam, though, we actually ran into a few artifacts that we didn't actually see in lab testing. These only showed up on Sky, mainly because we had some issues trying to get in-focus images in the lab of fake artificial stars. But we did find these things, which are vampire pixels. So they're like defects inside silicon that sort of suck the blood or the charge from pixels around them into a central core, and sometimes it can do that enough so that it actually starts saturating and bleeding in the center. The other thing we discovered was phosphorescent wax, which is left over from the vendor that put this wax coating on top of the CCD and then cleaned it off, but didn't do a perfect job of cleaning it off. So when this gets exposed to light, it can emit its own light at a lower wavelength for some few second time constant afterwards. And then the other thing we found were these ITL dips. So ITL is a specific sensor type that we have on the LSST camera focal plane. And When you have a really bright saturated star, what you can get is a trail of a dip in the charge that can span the full range of the CCD. All of these effects that we found pretty much only affect these ITL type detectors. On the full LSST camera focal plane, we have two different vendor types. So we have the ITL ones, which we put on the outside, and then we have ones made by Teledyne E2V that we put on the inner part. This is, we have in total, we have the 189 science sensors. This is sort of the map of this is sort of like the fictional map of the LSST camera focal plane. The center E2Vs tend to have what we found, they're an easy thing to remember is they tend to be lower in every aspect. So that means they tend to have lower noise, lower saturation points, fewer defects, lower charge transfer inefficiency. The only exception is they have 2 times the brighter, fatter effect. But there's also a few dead amplifiers, one small scratch here, but in general, we're actually only masking about 0.5% of the entire focal plane as physical defects. Some of the instrument signatures that we found, like this one sensor with signal-dependent correlated noise, we've actually fixed with sequencer updates, which are different modes of operations of the detector. For a lot more information about the operation of the detector and things we've learned about our own sensors from in-lab testing, you can see that Sitcom tech note. It's 300 pages and it's probably more information than you'll ever want to know. But if you want to know anything, you can go there. And then last but not least, for ISR, giving you an idea of where we're headed or what we're currently doing. So right now we're in the process of standardizing the actual calibration generation side and also standardizing the process of deploying calibrations. We're also developing visualization tools to visualize the literally 500,000 plots that we have of metrics and quality assurance verification metrics to analyze all the 3,000 something amplifiers across the focal plane. The other thing to note is for ComCam, we didn't have the calibration system fully installed inside the dome, but now for LSST Cam we do. So that means we have a larger range of different calibration data sets that we can use to, including taking in-dome flats, monochromatic flats, and sort of laser spot-like measurements across the focal plane to conduct more detailed and comprehensive analyses of the LSST camera system. In the future, we're implementing new corrections for things like fringing, tree rings, and photometric calibration of subdetector QE variations that depend on the SED of the object. But we're doing really well with our system, our science requirements, which Eli and other people will talk about next.
Thank you, Alex. Now I'm going to talk about photometric calibration once it comes out of ISR. If you go to the algorithms workshop, you'll hear all about the forward global calibration method, which we use for HSC, Lattice, ComCam, DP1, and now LSST Cam. I'm going to show some tests on the 225-40 field that Yusra talked about. And this is the surprise she alluded to was some of my code was not expecting a 250,000 good high quality observations of stars on one visit at a time. And for a couple of the metrics, it was trying to use all of them at once that it didn't need to. It could downsample comfortably, but never hit that with DCAM. So we have this data is from about 25 dithered observations per filter with rotations on May 23rd. The part that I was starting with was building an illumination correction for the response to focused light. And what you find is the fit was grinding away on flat field gradients. So another surprise is that, is this a surprise? It's very hard to flat field this giant thing as we're commissioning the whole system. And so I've been spending a bunch of time working on this, but in the G, this gradient is entirely put in there by alignments in the flat field system, which we have improved, but there's still more work to be done. And here in I-band, it's plus or minus 15% across. So you really don't want your flat to be putting in a big gradient like that. That's one of the big dangers for creating little step functions and terrible things in your photometric calibration. So FGCM does a full forward chromatic solution, and it needs to know the instrument, and we have previous lab-based quantum efficiency as a function of wavelength. We have filter scans from the filter vendor, Materion, the triple silver mirror coatings to predict the throughput. And here on the left is the I-band response measured from stars. And this chromatic term is if you take a red star and a blue star, if you took them from the middle to the outside edge, they would move relative to each other by a few percent relative to each other. That's the chromatic part. And much of this is radial difference in the filter throughput. And the middle is the model of what we get from the filter scan and the QE scans. And here's the residual, and it looks really good. So our scans so far are in the I-band are excellent. In the U-band, here's an example. You can see on the left what the stars are saying. There's some radial evolution in the filter, and in the middle is our prediction. Now these are smaller scales. This is only a couple percent, but our QE measurements in the U-band were not so good. So we have much better ones. So we also have estimates of photometric repeatability. Now this is on a single night, an excellent night. But this is so far just using signal to noise 1,000 star observations. And each of these plots, U and G band, I have all of the stars. These are 10% reserve stars from the FIT. And then the 25% bluest, middle 50% and 25% reddest. And there are no red stars that we see in the U band. And the total width of these histograms is something like 4 millimags, and the intrinsic component is smaller than that. When I run this again after fitting the other stuff, I'm going to use higher signal to noise stars to test. You can see there's plenty of stars to go around. And so again, R and I, everything looks excellent, as well as Z band. So we're really hitting our targets here. And a little secret from back in the DS days, if you've ever seen me talk about my DS calibrations. For DS, I never could get, and in HSC, never could get the red stars in the G band to look anywhere close to the rest of them. And it just worked out of the box here. So I think that's a tribute to the scans that we have and the excellent work from everyone who got all these inputs. But we can do better. So we can remove the gradients. We have the collimated beam projector. We have QE scans analysis ongoing. It looks very good so far. And this is in the next month or so, we'll be updating that, and actual good U and adding in Y to all of this. Turning on the illumination corrections, which will simplify the initial prompt processing and rapid analysis. And then we also have the collimated beam projector for filter scans, but that is more than a month. That's talk to me about angles of incidence.
Hi, I am Pierre-François, and I will talk in behalf of Claire Saunders for astrometry. So for the astrometry, we are using GBDES for getting our final astrometric solution.
Right now, if we look at astrometric repeatability metric, we are close from our target and the requirement. But the thing that I will show in next slide is like there is still a lot of room for improvement in our astrometry. And I guess we understand really well what we have to do. So I guess the first things that is really nice we can see is like if we look at astrometric residuals map at single visit level, you will see like stripe patterns that are consistent with atmospheric turbulences. And this is something we expect because this is not something in our astrometric model. And this is something already observed in DES or HSC. And so some of the work that Claire started is like, we know we can get a model of those atmospheric turbulences using Gaussian processes. And you have an example of a Gaussian process model of those astrometric residuals, and you are able to get most of these patterns. And this is something that Claire is working on to implement into the pipeline. Another thing we know of is like sensor is introducing astrometric distortion. And if you are stacking those as a single visit astrometric residuals across all the science visits, you can start to see like defects from our sensor. And you can see like there is clearly like two different patterns where you have the ITL chip and where you have the E2V chips. And this is really nice that by stacking residual, you start to see like all the defects from the sensor. And there is a plan also like to include that directly into the astrometric solutions. And something also that GBDES can do is like fit directly from the data a camera model. And so here is like something that Claire did of fitting the camera model directly from the data using GBDES, and to compare that from the input camera model. And there is clearly a difference, but it means that by injecting directly like the camera model from GBDES, you can improve also our astrometric solution. So it's not implemented yet into the pipeline, but it will. Like so. Okay, so I'm done with astrometry, and I will switch to point spread function modeling. So for modeling the final point spread function, we are using PIF, where the model will be done like per CCD. With a propagation of the point spread function on a single visit level with a second order polynomial interpolation, which is different from what was done on DP1 for LSST ComCam. And I will explain why in a few slides. And what I will show is mostly like PSF characterization and some physical effects we start to understand. And there is a more detailed talk I will give about that on Thursday, if you want to know more detail. But here, what we can see, this is a stack of average PSF size across 3,000 visits of LSST cam. And you can see like you have a lot of structure across the focal plane. You have like a characteristic blob pattern on ITL chip. You have some rectangle step function you can see on E2V sensors that are where the amplifier are. And there is a ring pattern on the edge. And I guess now we mostly understood what is going on when we are seeing all the structure across the focal plane. The blob pattern is due to ITL 8 variation. I will talk about that. I guess the rectangle and the ring pattern are mostly due to background subtraction. And also there is like a brighter fatter overcorrection. And what we don't see here, and I will talk about, is like the color dependency of the PSF and the atmospheric turbulences. So I was talking about like this blob pattern on ITL 8 variation. And here, this is another way of seeing PSF residuals by kind of doing a zero order interpolation. And the thing is like you can see like there is a characteristic like ring circle patterns. And if you compare that with measurement in the lab at Slack on 8 variation of chip. You can see that the pattern looks to be correlated with the 8 variation measure in the lab. So like the blob pattern on ITL chip is really due to the fact that the CCD is not flat. And oh yes, and you can make a correlation between both, and you see this is totally correlated. And we are currently working on implementing that directly into the PSF model. Yes. So also you have so we understand the blob pattern on the ITL, but there is still like the ring and the rectangle. I won't comment why it's because of background subtraction. Come to my talk on Thursday. But I guess an easy way to see that is by removing a faint object that will be more sensitive to that. And if you remove faint object in that plot, you will see that most of the structure are disappearing. But you start to see other features that are CCD dependent. And that is the following of my talk. Because like you have like CCDs that looks to have stronger residuals than others. And I guess this is due to brighter, fatter overcorrection. So if you look like PSF residuals as a function of flux, you can see there is a clear dependency, and it depends if you are on the ITL chip or in E2V chip. But if you look the way the dependency is, it's not really a brighter, fatter, it's more a brighter, thinner right now. And to be sure, this is due to brighter, fatter. On a single CCD, on a E2V CCD, the detector number 42, I switch on and off the brighter, fatter correction. So in red, this is without the brighter, fatter correction. And in blue, this is after the brighter, fatter correction. And you can see there is kind of over correction on this. And there is a lot of work going on to try to understand more this effect and to try to correct for that right now. Okay. Another thing is like PSF is supposed to be chromatic. So here it's not on LSST cam, but it's on DP1, on LSST cam, where I bind in different color bin the dependency of the PSF with magnitude. And you can see like there is like a gradient that depends on color. And right now in the in the Science Pipeline, we implemented a DES year 6 style PSF color correction. And if you implement this color correction, you can take most of the effects and remove most of the dependency. And to finish, I guess this is a plot that I like to see. Is like if you look just at the single visit level, how the size and ellipticity parameters varies across the focal plane. You can see like there is a smooth gradient across the focal plane that is due to the optics, and you can see that in most of the visits so far I see. But also like you can, especially like in E1 ellipticity, you see like a stripe pattern that is likely due to the atmosphere. And if you look now at PSF residuals at the single visit level, you can see that there is still like remaining stripes across the focal plane. And that is due to the fact that because you are modeling the PSF at the single CCD level, a second order polynomial interpolation cannot catch that. So you need a full focal plane solution to get that. And there is a plan of implementing this in the future. And I guess I am done for PSF.
Hi, my name is Mario Juric. I'm going to tell you about the solar system discovery pipeline, but I just want to make clear that these slides were made by Jake Kurlander and Ari Heinz, who weren't able to be here. So I'm just speaking to their slides. It's really all the work is theirs. So solar system discovery pipeline, as the name says, its goal is to discover moving objects and to link them into solar system objects in primarily image differencing data. The eye chart we have here before you shows you the state of the pipeline, and green is good and blue will be good. Green means that we've developed those pieces and they're actually running. And what I want to point to is this big box here, which shows you essentially the entire pipeline running to discovery of asteroids within the Butler/task system that Science Pipelines have. That's essentially complete. And I think as of last week, we've ran first runs in this mode. The algorithms have been ready for quite a while. We've used them at RFL. I'll show you that in the next slide for Rubin First Look. But what's new here is that now those algorithms are working in the same way with the same task framework as the rest of DM. It wasn't an entirely simple task. This took about 3.5 to 4 months to wrap in our middleware, but we got it running, and in the meantime, or while doing that, added some improvements to the task system to be able to make these kinds of runs that the solar system pipeline needs. So if we move on to the next slide. Oh. There we go. We moved on to the next slide. The core of the pipeline are the algorithms, and the core algorithm we're using is called HelioLink. HelioLink finds pairs of objects in each night that might belong to moving objects, and then identifies at least 3 pairs of objects in a 2-week window to link them together to fit a Keplerian orbit and declare that combination belongs to a solar system object. So this was first tested on real data using the Rubin First Look dataset. And the short summary is that it worked. It worked well. The longer description is here on the slide. And what I want to show you with this is that it worked well for RFL, even though this data set is essentially the exact opposite of what we're going to have in YFAST Deep. So RFL used roughly deep drilling cadence, not the cadence that HelioLink was optimized for. Still, the code had no problem with deep drilling cadence. We had anticipated this and designed in flexibility in tracklet creation so that we can create not just tracklets made out of 2 points, but also made out of hundreds of points, which is what we have in Rubin First Look. And that also helped in certain ways, because if you get a 100-point tracklet, that's almost impossible to get by just chance alignment of artifacts on the camera or software created artifacts. The total take of asteroids, if you're from the Solar System Science Collaboration and you're looking at this and thinking, is this roughly what I would expect given the simulations originally? The numbers were slightly smaller for 2 reasons. One is the effective flux limit came short of the 24th magnitude that we nominally expect once we are in operations. So that will change. It should get much closer in the future. And then the second thing is, if you do these naive calculations of how many asteroids am I supposed to see around opposition, this field was closer to quadrature than opposition almost. So asteroid phase functions fade rapidly away from the anti-solar point. That makes them much fainter, and that's the other reason why there weren't as many as you might expect with just back of the envelope calculation. The other reason was that we used very conservative criteria for public announcement. There are more objects in this data set. We announced about 2,100. There are many more in there. We just, for the public announcement, wanted to be sure that we submit only the real ones. Some fun details about the algorithms. The way the algorithm works is you assume that objects are at a certain distance, and then you try to find all observations that match that assumption. Turns out that assumption can be fairly loose. So even if we assumed objects at distances of 1.5 AU or more, we still found a whole bunch of near-Earth objects that come closer almost by accident, quote unquote. The last things I'm going to end on is that RFL observations are not a real test of HelioLink. We need wide-fast deep cadence. That is what we're now finally getting with the SV survey. So we are incredibly excited to run this on SV and are looking forward to templates. We're looking forward to single visit detections, where things always take a little bit longer than you expect when commissioning. So we're finding creative ways to accelerate the parts in testing, at least the solar system side of things. So if everything works well, we hope to have many, many more linkages and discoveries over the next weeks, 2 months. And I'll finish with this code being run far outside of its main design context, but still performing well. And it's a real credit to Ari Heinz, who is the primary author in this, that we were able 2 weeks after first look to find, 2 weeks after the first ever image, to be finding on order of 2,000 asteroids from this imaging. So thanks all.
All right, next, Bruno Sanchez online is hopefully going to speak to difference imaging. Bruno, I'll advance your slides. Do you want to unmute?
Yes, thank you. So my name is Bruno Sanchez. I'm a member of the other production team that Eric and Ian lead. And so I'm based in France, but I work very closely on the difference imaging analysis technique. So here is an illustration for telling you about what this technique is doing. So this is the primordial and most important technique we have for discovering variability in the LSST. We use it for detecting changes in brightness and also changes in position. And how it works is basically we use data from previous nights to build a very deep coated template, many images stacked, and then for each one of the new freshly taken visits images, like the one in the middle, we perform a pixel by pixel matching equalization algorithm that can obtain differences and hopefully only remains in this difference what has changed. So here I'm showing you, and you can find this data in the LSST ComCam DP1 release dataset. This is one of the many difference images that we have in this set. It's like you can see very good quality. We're getting very good results. You can also see some features of it, like for instance in the Bayer-Bike star that has spikes in the template on the left. You can also see probably some residuals or saturation in the core, but fear not, we have a very complex and able tools to mask these pixels and provide information about what the technique is doing. So in order to validate this in an instrument that is also during the commissioning phase, we use synthetic source injection. So in the next slide, I'm showing you this very same image, with 4 synthetic sources that we have injected in this case. And by the way, this is a ECDFS image that you're looking at. So these 4 sources are part of a much larger sample. You can see them in the red markings over here. In the next slide, I show you distributions of the brightnesses of all the injected sources in the DP1 campaign, which was roughly 1.5 million sources. Most of them were point sources, and they were used for validation, like I said, of the DIA difference image analysis pipeline, and also for building the training set for machine learning vectoring pipelines. So the main metrics that we extract a large number of metrics from these. And there are many important ones. The main one is the next slide, where I show you the completeness or the fraction of detected objects as a function of the signal to noise ratio of these synthetic sources. So you can see how we are reaching 50% completeness at about 5 in the signal to noise ratio parameterization space. And this is very important for us because this is the main validation tool that we have to understand whether we are detecting important the old sources in the images or not. In the next slide, I'm including as well a table. So we have the integrated completeness for signal to noise ratio greater than a certain value. And in the requirements, we have requirements imposed for the 6, for the signal to noise ratio 6. And we exceed these requirements with a completeness of 98.5. Again, this is in the ECDFS sample. And we also have a larger campaign in all the other fields in DP1. Next, we can also, in the next slide, we can also recover parameters and measurements for these sources. Here I'm showing you the astrometric residuals in a two-dimensional histogram, and also for right ascension and declination. And if we look at the residuals of sources that are with signal-to-noise ratio greater than 10, we can see that we have a 0.02 much in dispersion normal distributed residuals. So we're confident that we're doing good astrometry of these sources. And finally, in the last slide, I'm showing you our photometric results, where I show you the offset in magnitude in the y-axis for our fakes injected in the I-band in this ECDFS field. And on the right side, I'm showing you the pulse or the fractional flux bias of these sources. So I'm showing you here as well that up to magnitudes 22.5, if we look at the residuals, we have very well constrained residuals on magnitude with scatter that's lower than 0.04 magnitudes. So I leave you with that. There's many more metrics that we have in the pipelines, but this is one of the validation systems that we have in place. And yeah, thanks.
Is it work? Yeah, it's working. So my name is Tatiana Acero Cuellar. I'm going to talk about the machine learning model that is showing the reliability score for DI sources. So the first thing I want to say is that this, so in maybe more modern terms, the reliability score is the real bogus score. But as the name said, it's a score between 0 and 1 that we can interpret it as the probability of the source to be real. So the input of this model are the three images, the template, the science, and the difference image. Then we have three convolutional layers and a couple of linear layers. And as I was saying, the output is a number between 0 and 1. That is like the probability of the source to be real. So if you are asking, or if you're not, I'm gonna tell you either way, why in the era of transformers, generative AI, I don't know, you name it, do we have a model like this, a convolutional neural network? It's because this score is part of the alert products. So that means that the time that the system took to like calculate this score, it's counted within the 60 seconds the system is going to have to release the alerts. So this model was designed in such a way that the inference time can be made in less than 24 milliseconds per source. So that's why. So this model was initially trained using DC2 data with some fakes. And then we are using this as a base model. And then we are fine-tuning, or we fine-tune the model using LSST CompCan data with injections like the ones Bruno just showed. And so the performance for this data set that contains the fakes, it's really good. We are like above the requirements, the purity and completeness requirements. But we don't live in a simulated world, so we need to test against real data. So one way to do that is to do some cross-matching with existing catalogs. So one that was kind of straightforward to do was to see the solar system objects in DP1. And so the model is performing really good for the asteroids in DP1. But then we have transients and variable objects. So a few months ago, internal labeling service called TASO was launched on the USDF, where people with access to ComCam data label a bunch of ComCam images. And we were able to identify some transients of variables. So as you see on the plots with transients, we are reaching a 74% accuracy, which is okay, but we can do better. And with variables, it's really bad. It's 4% accuracy. And I have to say that, so there are a lot of issues when you try to test against real data. For this particular case, we have the labels are kind of noisy. So especially for the variables, we don't really know how many actual variables do we have. So some next steps is that we can do more cross-matching with other existing catalogs like TNS, Gaia. And then the idea is that we're gonna eventually launch a very large Suniverse campaign where people from all the community can help us to have more labels. And also the other issues that the injections that we have used so far are transient-like sources. So the idea is to also inject variable-like sources into the data. And that's all.
Thank you. Okay, so you saw completeness and purity on the difference images, but Dan is online to introduce completeness and purity of detections on the coads.
I am. So we've done this in a couple of ways. This plot is coming from the DP1 paper. So what we've done is essentially do object injection, pretty much the same way we do source injection, except we're putting in both stars and galaxies, parametric models of galaxies, into the coads before we run detection, and then we run through the whole pipelines again. Here are the input properties of both the stars and the galaxies are drawn from the DC2 input catalogs. So this is essentially a replacement for the regular reprocessing we've been doing and are still doing of the DC2 images themselves. The reason we want to do this is, of course, we want to measure the completeness for different types of objects, both stars and galaxies, galaxies being to first order harder to detect at the same magnitude because they're extended. So this is from basically a small, well, a subset of the patches in ECDFS in that tract 5063 that has the most data, basically where the data are deepest. And we've had this nice completeness as a function of magnitude. So when we start doing this on a more regular basis, and right now this is basically done on an ad hoc basis to include in the DP1 paper. In the future, we expect to probably do this sort of thing for all of the deep fields and perhaps a representative sample of some of the other fields, certainly not for the whole survey because that's computationally prohibitive. On the next slide, which I didn't actually add myself, but Yusra, if you want to say something about this, you can.
I put it in there to compare your completeness metrics from source injection to that, which is predicted just using characteristics of the single epoch images that went into the coad. This PSF maglim is the estimated 5 magnitude limiting depth of point sources, whereas Dan was showing you the completeness for galaxies.
And we should at some point compare those numbers. We can also do injections just of stars of larger numbers than what are in DC2. I kept the number of stars to a realistic amount just because I was more interested in what came out for the galaxies. But okay, we're also doing comparisons by matching with external catalogs like Euclid Q1, because there is data there in ECDFS. This is showing only stars instead of the previous plot, which was only galaxies. And we see the purity is quite high, down to 25th magnitude before it drops off. You may have heard, actually, the Euclid data is slightly shallower than ours, so this is not unexpected. The other thing you can look at is the classification. Have we classified these objects correctly? And in that orange line, what you could see is basically everything we call the star fainter than 23rd magnitude is also classified as a star by Euclid. So at least we agree. And then at about 23.5, 24, the number counts rise artificially. This is just from the fact that we're basically misclassifying galaxies as stars and vice versa. And then on the next slide is, I think, just the same plot as 2 plots ago, but for the Euclid Deep Field South. All right, on to a completely different subject. This is PhotoZ. These are very preliminary and speculative results. So what we are doing, we have a package called MEJ-PZ, which is likely to be renamed, which is not yet in LSST distrib in the main part of the packages that are included in the Science Pipelines, but will be by DP2. And what this is essentially an interface to the desk rail codes. And what we're going to do for DP2 is run a couple of these algorithms and put the outputs in the object table. These are not the only PhotoZ products that will be produced. There will also be a whole host of different algorithms and measurements run by Linnea alongside Desk using Rail. So what I'm showing here, what we're planning is to have basically 2 algorithms that are sort of representative of the ones that cosmologists will be using. One is BPZ, this is template fitting, and the other is KNN, which is a relatively simple machine learning type of model, as actually Gaussian mixture model. Okay, I don't expect you to read all the numbers from this, but the point is this is showing basically the scatter in the PhotoZ from a sample that was put together by Eric Charles in the PhotoZ science unit for different flux measurements of the same sample of galaxies. So that includes HOP, which is more or less designed to measure consistent colors for PhotoZ, PSF, 3 flavors of galaxy measurements, including 2 forward models, the C model and CIRSIC. And yeah, so the science unit has written a tech note about this, which will be a paper as well. You can go read the tech note now. Melissa Graham is essentially in charge of the PhotoZ aspect of this, and she has been writing some documents about how you can access these data for DP1. I'm just going to say they're unofficial in that they're not provided by data management, so don't ask DM people how they're made or how to access them. You'll see that information in those docs when Melissa is ready. So on the next slide, this is the same chart showing basically just a different metric, the fraction of outliers rather than just the scatter. And so the interesting thing from this, at least from my perspective, is that the 3 algorithms we expected to perform well for this, that's HOP with a 1 arcsecond aperture, C model and CIRSIC, perform more or less the same. Some PhotoZ algorithms prefer one flux algorithm over the other. One that I included there, FC Boost, appears to be the best performing machine learning based one, but it's probably not one. It's more complicated, so it's probably not one that we're going to run as DM and including in the object tables. The most interesting thing I found is that the template fitting code BPZ seemed to be happiest with PSF colors, which was quite surprising because obviously they're not intended to measure galaxy colors, but nonetheless, that seems to be what happened. And there was sort of a broad trend where machine learning based algorithms performed better, but this is them having been given a representative training set. And I've been warned this probably won't hold true for broader samples where we don't necessarily have a full representative training set. And there we might expect the template fitting codes like BPZ to do relatively better, or at least about the same. And that's all I had.
Okay, for the final algorithm we're presenting today, update on shear and cell-based coads. The plan is to run meta detection for data preview 2 and build cell-based coads. So we've spent most of our effort building shear-ready cell-based coads, and this is now running in the pipelines regularly and still needs a lot of testing and validation. Now we're working on integrating meta detection itself into the pipelines. Cell-based coads basically divide each patch into 150 by 150 pixel cells. And we consider the PSF models and the visit propagated calibrations approximately constant over that cell. So this enables us to speed up all the measurements on our coads, which is currently a big dominating factor in wall time of pipeline performance right now, because we have to evaluate the full stack of PSF models for every galaxy. And so Aaron Sheldon threw us for a loop this past year when he showed us that simulation work showed that shear measurements are insensitive to PSF model errors caused by edges, and that it's in our plan to make small cell edge-free coads, the edge-free part of that isn't entirely necessary. So plan now is to still make cell-based coads, but the plan is for them to no longer be edge-free. So to guard against rare cases where this assumption might break down, the coads also will include a diagnostic image plane that reports the difference between the true PSF and the model due to edges. And this also means that our switch to cell-based coads is more about how we represent the PSF as constant over a cell, rather than a change to the actual content of the pixels themselves. The benefit of this is that the coads will be approximately the same, but will be better characterized and more efficient. And hang on. Okay. One of these, I'm blinking between the two. One of these is the original per patch coads, and the other one is a mosaic of the cell-based coads. Can you tell the difference? Yeah. Okay, so the second one is the cell-based coads, and the grid looked something like this. Now right now these are edge-free, and so there is a slight reduction in the number of visits that went into them. And you can, if you look on the Google slides, you can see that there is a slight increase in noise in the cell-based coads, but you cannot see any boundaries on the backgrounds or anything. So rest assured, this will be fine. Okay, wrapping up. So some sessions with Pipelines team members coming up. I know Eric had a bunch yesterday. You can hear more about PSFs from Pierre-Francois on Thursday, more about Solar System with Mario on Thursday. I'll be giving a short plenary on Friday, and Eli will be talking at the photometric calibration session on Friday as well. Please cite our pipelines paper. Some references that I use every day if you want to find all those quality assurance scientific performance plots that we showed. You can find them on ls.st/monitoring. We have a variety of QA tools that we have used during commissioning, both during ComCam era and LSSTCam era. If you want to know where to find the Butler collections, where the data release production, the processings are, if you're on the commissioning team, take a look at ls.st/campaigns. The campaign management team maintains some information on the ongoing processing campaigns there. And then finally, Lee Kelvin maintains PDFs of the pipeline graphs for all the cameras that we have currently run in regression and continuous integration testing there as well. So finally, okay, so to summarize where we are in midst of pipeline commissioning right now. Many of the performance metrics have met their design goals and the rest are on track. Our goal isn't just meeting requirements though, it is providing state-of-the-art algorithms through operations. Most of us are going through into the operations team. And so we will be here next year and alongside you for all 10 years, incorporating your feedback into the pipelines and tracking state-of-the-art. We will be here next year to give this same talk as usual, and hopefully by then we will have released data preview 2 and can talk about pipeline performance in data preview 2 and the wide fast deep data that is in progress at that point. If you were at the early science session this morning, you would have heard that we have refactored our data release schedule so that there will be a 90-day period after we release data preview 2 next summer that we can incorporate your feedback. But you don't have to wait until then because data preview 1 is out right now and it's in your hands. And we are taking feedback now. That feedback, there's still time for it to be incorporated into data preview 2. Deadline for that to be getting that kind of feedback to be incorporated into data preview 2 would be November of this year. And yeah, take a look. It's in your hands and you don't have to take my word for it. Thank you. Okay, we've got 15 minutes for questions and Irfan will help me get the microphones to you.
Hi, Sam Wyatt. For the slide that had the real bogus score for the DIA sources, there was an accuracy estimation. How is that calculated? Because it's a histogram of 0 to 1. So at what point do you say it's accurate or not?
Yes, so for the accuracy, we assume a threshold of 0.5. So everything that has a score below that is real and the rest of it is bogus.
Thanks.
Okay. You flashed very quickly a paper describing all of this. Can you bring that up again so that we can all, you asked us to cite it, so we have to know what to look for.
Yeah, we have a DOI, we're on ADS, and you can also find it at PSTN 19. It is still somewhat a work in progress.
I guess my question for Eli is, if you put the SNR cut where you did, I don't even understand why those histograms are as good as they are. Because at an SNR of 100, you'd expect the histogram to actually be of that order, right?
It's a little bit smaller, yeah.
So, and you sort of alluded to the fact that you're going to make that cut more stringent. So we're doing at least that well, right?
Yes, yeah.
Okay, great. And my question for the frame subtraction is, I don't understand why the discrimination algorithm was so different between transients and variables, because those almost sound like the same thing. Are variables things that have persistent variability in the time series so that they manifest in the template? Can you help me understand why that difference is so extreme?
So I think the answer is going to be more qualitative. So in the transient injection, you only have your PSF, your point source in the science image in most of the cases. But the variables has the point source in both the template and the science. So, and yeah, and the machine learning doesn't make magic. So you need to. Yeah, the input of the model is the template, the science, and the different images.
And these were also hand classified. And there was a lot of noise. So take a look through Tasso and try to classify some of them yourselves and see if you can.
Sorry, we didn't at that time have the ability to inject variables with the tools that we had. So the machine learning set was not representative, and we know that's an issue, and we are fixing it.
Hello, I'm Gregory from IFA. I'm wondering, I heard that you use the 3 channels to train the IP classifier, right? And so I wonder, how did you inject the pointers on the image? So I'm working on the strategy about point source injection. So our preliminary literature shows that if we inject the sources nearby galaxies, the transient classification performance is better. But if we just randomly inject point source in the image, then the asteroid performance is better. So maybe that strategy differences may affect your transient and asteroid performance. So which strategies did you use?
It was Bruno who presented the synthetic source injection on difference imaging, and so he's the best person to answer that question.
Got it.
So maybe I can answer that. So basically we have, if you can also go back to the slide, Yusra, because there's a plot on this, but in our injection runs, we have 2 populations of injected sources. Nope, the photometric precision ones, because it's there where we have the distributions. Next and next, I think 2 more. One more. No, 1 extra more, sorry. But here, right, the top panels are showing you the actual true distribution of the brightnesses of our sources, and you have a combination of hosted with galaxy hosts and hostless randomly distributed in sky coordinates transients. And they also have a different distribution in brightness. So one of them actually is correlated with their host brightness, and the other one is not. The sample that we are missing, though, is variable stars. And given how DP1 was processed, which was a DRP processing, so it means that we have the template sometimes has the flux of the variable stars and some of the transits that may be there in the template. So there's a lot of negative transients, and it's more complicated to get that population covered. Hopefully I answered your question, but to summarize again, we do have transients which are hosted and hostless.
Yes, the host contamination may affect the leisure, but what I'm trying to address is the model will see the contextual information if we put the 3-channel images. So the model may consider the existence of host galaxy nearby the point source that we injected. That may affect the leisure. That's what I'm trying to say. But I will send you the email later, so we will talk more details. Yeah, thank you.
Sure, thanks to you.
I also have a question for Tatiana, popular, about the real bogus reliability score. So I have 2 questions. The first is a very basic question, which is, how is it going to be used? Is that how you're deciding which sources to put out, or are you just are you giving this number along with the output so people know how to use it? And the second question is, I'm sort of confused by, since this is a convolutional neural network, you have to train it. So you're putting some source injection in. So how do you decide what are the true sources and what are the false sources? Do you take all the sources that are found by the source detection algorithm and look at them and sort them? Can you say something about how the training actually works?
Okay, so the reliability score is assigned to every DI source, and so far we don't have any plans to suggest, but Eric can confirm we don't have plans to suggest any threshold. So the idea is that each science case assign the best threshold for the case. And about the like the labels with the injections. Yes, so we label everything as real if the thing that we injected was detected by DI. Yes, so everything, so yeah. So yeah, so for the with the injections, everything that was detected and was injected, it's real, and the rest of the things that were detected by the IA, but they don't fall like we did in any injection, are bogus. And yes, there is some contamination of reals in the bogus, but it's very minimal. I will say like what 1% maybe of contamination. I don't know, Eric, if you have.
I think there are more rails than that without filtering, but we're also thinking about, you know, more active learning approaches and labeling to sort of, you know, the injection is an efficient way to do an initial training bootstrap a model, but then you need to, you know, check your labels and make sure that they're good. And so that's a process we'll be working on going forward.
Hi, can you speak to how the pipelines are performing in crowded fields?
Is Lauren online?
Yes, I'm here. That's a bit of a tricky question.
It's either between you or Yumi.
I'll start and you finish. You fill in the blanks I leave out. So it's a bit of a tricky question. The pipelines are not optimized to be easily run on crowded fields. So one of the issues is our detection thresholds when we're detecting PSF stars are too high when it's a crowded field. So basically we detect everything and everything overlaps each other, and then we have no stars. Despite it being a crowded field, we have no stars to do our PSF modeling with. So we have some ideas on how to improve things without having to have bespoke pipelines that have tuned parameters. So for example, that Trifid Nebula first look image was all bespoke processing that I did, that I tweaked parameters to get everything to pass. And we're hoping we can develop some kind of dynamic detection thresholding such that we don't have to have different sets of pipelines with different configurations. That's very much work in progress. It's finicky and tough, and validating is tricky. And it's maybe behind some of the other advances in pipelines because we didn't have very many crowded data sets to start testing things on. But now we have plenty, and the hope is that we will do a bit better. As far as because the question of how well are we performing on crowded fields has many levels to it. The part when we do succeed, we do reasonably well on the stars that we do resolve, and when we have detections that when we go through to the coads aren't completely blended and therefore skipped because we have a threshold on how many peaks we can blend at a certain time. The metrics look really good, but again, that's not going into the deepest, say, for example, the center 47 tuck. We don't have metrics for there, but DP1 should have some stellar loci for the outer parts of certainly the outer parts of 47 tuck, and I'm not sure how much coverage in 4NX because I'm not sure it had 3 bands as well. So we're working on it. We're doing okay, but we want to do much better. Bespoke processing can recover things, and we hope to move beyond that.
Or a quick follow-up question. So like the Center 47 tuck not being able to be processed, was that primarily a pipeline issue or an issue with like the observations themselves, like the stars being saturated or something like that?
The center of 47 tuck is saturated in LSST. And also, yeah, so there are two crowded fields in data preview 1 that you can go explore and answer for yourself.
Well, it's late, so I have two questions. You can choose which one. So one of them is with this Nacho Sevilla from the Dark Energy Science collaboration. With upon release of DRX, is there an expectation of there being some kind of report based on analysis tools plots, or these are the metrics for this specific release, like some kind of report? And then the other question is about the shear catalogs. Is the expectation also that it will be shipped with the rest of the release with Rusio and all that as part of it?
Okay. Just for time, I'll take a crack at both of those. So yes, the plan for data preview 2 is to ship the shear catalog along with data preview 2. For the first question of what's planned for the data releases in terms of quality performance plots. So one of our precursor data sets was HyperSuPrimeCam, and the LSST Science Pipelines were used as the pipelines to make the data releases for the HyperSuPrimeCam public data releases. And if you go to those data release websites, you'll see that there's something in between the data release paper and the data access documentation, which is a series of quality plots in some different categories across the sky. And those plots are actually the ones that inspired the ones that I showed you earlier of different metrics over the field of view. And the plan is to include something like that for future data releases. The Tanaka-san plots.
Hi, one more question again, maybe for Eric. There's been a lot of talk about real bogus score, and I may have missed this earlier in other talks, but how much does that influence an alert going out from a DIA source? Is it going to be mostly the real bogus score, or is there going to be a lot of other factors that go into it as well? Is the 0.5 what constitutes it?
So our certainly our steady state goal is to not do any filtering on real bogus. We want to allow that to be left up to the user. I think we reserve the right, especially as we're commissioning, to make sure that we're starting off on a good foot and not overwhelming the brokers and our users with things we don't think are real. We do some initial rejection of stuff that we know is not salvageable, that is fully saturated with the core, for instance, or flagged by no data and stuff like that. But in general, we're trying to, in the spirit of the alerts, pass as much on as possible and let users sort of find the gems.
Right. It is 2:03. Thank you for coming to this session. Thank you for coming to this session. Ask us questions over break, please.